So this is the big three. Our big first three formulas. Now, let's find out. Well, actually, I want to say something first about gravity. Gravity is something that we use often. Why do you think physicists use gravity? Yeah, it's a constant acceleration. Do you know what the acceleration of gravity is? Good, 9.8. And so do things fall at the same speed or do they accelerate at the same rate? Let's see what some other people have to say about this.
Let's say Jack holds both balls above his head, and then he drops them at exactly the same time. What do you expect to see?
Well, they're going to hit the ground at the same time.
I expect them to both land at the same time.
Same time.
Same time.
I think they both will.
This one to hit the ground first. However, they will actually both hit the ground at the same time.
Why is that?
Science.
Yeah, science.
Now the black one clearly feels a lot heavier. So the standard misconception is to believe that the black ball will accelerate at a greater rate and reach the ground first. This year, many people had an idea that both balls would land at the same time, but they didn't know exactly why. I found there were some different misconceptions. For example, many people seem to think that as an object falls towards the Earth, it falls with a constant speed. From this height, yeah, pretty much. It's just constant speed all the way down speed.
Yeah, I think it'll be the same constant speed.
I think it's constant.
I seem to remember it being constant. I did decently in physics, and I seem to remember that's the answer.
Whereas the truth is, the speed of both.
I love that. I did decently in physics, and that's the answer. Do things fall at the same speed? Pick something up on your desk and hold it just above your desk. What is its velocity right now? Zero. If you let it go, is it going to stay at zero? No. No, so things don't fall at the same speed. Okay? What do? They accelerate.
Balls is changing all the time. The balls are speeding up as they go towards the ground. That's what the force of gravity does on them. It makes them accelerate. It gets them to speed up. Another misconception I discovered was that some people believe both balls should have the same gravitational force on them, even though the black ball is clearly much, much heavier. The reason I think they said this was because they knew both balls needed to reach the ground at the same time, so they reasoned that the force on them must be the same. Tell me about how the gravitational force on this ball compares to the gravitational force on that ball.
The force is the same.
It's going to be very similar.
In terms of gravitational pull, they're both at the same, and they'll fall at the same rate. I'm not like Einstein, but same gravitational force around the whole world, right?
Because the gravitational pull on the Earth is the same on both objects.
Are you saying that the force on them is the same?
The pull is the same.
But you felt the pull, and you told me the pull is different.
No, I said the weight is different. I didn't say the pull is different.
It is heavier.
What is the difference between the force of gravity, the pull of gravity, and weight of the object? They are all the same. So the force of gravity on you right now is the same as the pull of gravity on you, which is your weight. If I put you into space far from the Earth, what happens to your weight? Do you weigh the same? No, you might be weightless, right? Does that mean that your mass changes? No, so your mass is the same. But the weight is the force of gravity on you.
And has more gravitational pull. But when I drop them, then they get equal with gravitational pull somehow.
Don't you think it's going to be like 5 times as much?
Yeah, you think, but it's not.
The way you're asking it, yes, but scientifically speaking, no.
The gravitational force on both these balls are the same.
Okay.
The gravitational force on both of these balls is the same.
Is that what you actually believe?
No, but it is.
Tell me what you believe.
I believe it should be more on this, simply for the fact that this is heavier, and just intuition tells me that it should be more, but after learning physics, we learned that it is actually the same.
I actually think the force on this ball is more than the force on this ball.
No, you don't.
I swear, I'm not trying to mess with you. So,
Like in real life?
in real life and in physics, I will tell you that the force on this ball is more. All right, ready? 3, 2, 1.
Yep, see?
Same time.
I would say the force on the medicine ball is like a lot more because it's got a lot more weight, it's got a lot more mass, but it's got a lot more inertia.
Oh.
You guys remember that, right? It's got a lot of resistance to acceleration, so it takes more force to get it accelerating at the same rate as this ball. And that's why they accelerate at the same rate. Thank you guys so much for playing along. I appreciate that.
Sorry,
Thanks,
Jared.
Chad.
So, the force of gravity on a heavy thing and a light thing is different. What's weird about gravity is that all of those different things, they all fall at the same acceleration. The acceleration of gravity is constant. The force of gravity is not. That's really weird, actually. That bothered me for a long time until I found the answer. And one day I will tell you the answer this year. But for now, what I want you to remember, the force of gravity is different on different things, but the acceleration of gravity is the same. Okay. So, it's our first formula. A is delta V over T. I've typed in here V2 minus V1, but you could also say VF minus VI over T. This is acceleration. And if you ever want to, if I'm ever doing slides and it's hard to see and you want to follow along, these are all on my website. You can go to the classroom and click on the website link, and you can follow along as you go, especially if it's hard to see. Okay, so here's a little question for you to try out this formula with. So what's VF in this problem? 16, yeah? So my VF is 16 and I'm going to subtract the VI. What's the initial velocity? 2. 2, good. So my change in V is going to be plus 14 meters per second, right? This is the time in this one is weird. You never see time written like this, but let's say you had a clock and it started at 1 second and it finished at 4.5 seconds. How much time has gone by? Yeah, 3.5. So the clock stopped at 4.5 and it started at 1. So the whole thing takes 3.5 seconds. So the answer is 4. How many people got 4? Okay, good. That's excellent. So our acceleration here is 4. And what is the units of acceleration here? So this is meters per second, right? So it's getting 14 meters per second faster every second. So you could say meters per second, or you could say meters per second squared, same thing. Could you have a unit of acceleration like kilometers per minute per hour? Yeah, you could have a thing like that. It would be fine. The SI unit is meters per second. Okay. This is our first of the big three here. Can you see that formula in the room somewhere? Lawrence has got it. Angela's got it. It's up here. So this is where we're going to start. And we're moving with our relationships that way. So this is the big number one. What's VF? Good. This is the final velocity, so the velocity you end with. And VI? Initial velocity. So this is the velocity you started with. What's A? MC? Good. Acceleration. And T? Leo? Good. Time. So what's the units of acceleration? Meters per second, and time is seconds. So when you multiply these, you end up with meters per second, right? And that's going to give you, and this is also meters per second, so your answer will be in meters per second, so that's kind of nice. Okay, let's use this formula for a little question here. Make that bigger. Okay, I went to Spokane one time and I watched this baseball game. It was like AA. And the pitcher's name was Chuck Fast. Kid you not. He's my favorite pitcher ever. He wasn't very good, but he didn't make it to the majors. But I love that his name was Chuck Fast. So this is maybe a little bit hard to see for some of you. So what's this? It says Chuck Fast throws a baseball with a velocity of 45 meters per second. So what's the 45?
Is it additional velocity?
Yeah, so this is VI is equal to 45. That's what you start with. So when the ball leaves his hand, it's going 45. And then it says it accelerates at a rate of -4 meters per second. So MC, what is this? Good, yeah, that's the acceleration. Say that one more time. Is it squared? The unit is squared, yeah, for sure. So this is -4 meters per second squared. What is -4? What does that mean?
Slowing down.
Stefan, say that again. Good, it's slowing down. So if you think of a pitcher throwing the ball, and the ball goes, and the catcher catches it, where in that flight is the ball going the fastest? Yeah, right as it leaves your hand, it's actually going the fastest. That's where they used to point the radar gun at where the catcher was, because they thought the ball would speed up as it went. But of course that doesn't happen, right? As soon as it leaves your hand, it starts to slow down. What is it that's slowing the ball down? Yeah, it's the air. It's the air. If you were on the moon and there was no air and you threw a baseball, it would not slow down. It would go the same speed the whole way. It would fall to the ground, but It wouldn't slow. So this is due to the air, and this negative means we're getting slower by 4 meters per second every second. Okay. It doesn't take much time. This is a really fast pitch. It's only 0.2 of a second. Okay, and we're wondering what is the final velocity. Hey, Polly. He's around. Yeah, he's around. He's. Oh, I want to check too. Okay, thanks. I appreciate that. Yeah. Yes. Where are your hands up?
Yeah. I'm wondering, does velocity go in meters per second or meters per second? Is it always?
Velocity is meters per second. That's it.
It's never per second, or squared, I guess.
No.
Okay, got it, thank you.
If it's squared, then it's acceleration. MC? Do you round it? Yeah, probably. Well, let's do the question. So VF is VI plus AT, right? So you start with 45, and then you're gonna have -4 times just your 0.2 seconds, right? So you're just taking off -0.8. So I guess this would be 44.2. That's your VF. Technically, you're right, MC. You should round that to 44. Yeah, I won't do it here, but I should have made this. I should have put another 0 in here for my sig figs, but I'm not worried about that. Who here got 44.2? Excellent, good. You're on track. I'm filming this, so you can check this later if you want. Okay. This is formula number 2. You can see it up there. So this time our velocity final is squared. Our initial velocity is squared. And then we have 2a. A is acceleration and d is our displacement. Rather.
So in acceleration, when it's meters per second squared, the second squared doesn't affect the equation at all unless you're doing like unit conversions, right? Like, would it affect it if you have to do unit conversions?
I see what you're saying. So
So I'm not sure.
let's say that my best advice for you for Physics 11 is to, if you ever get if you get a velocity in kilometers per hour, just convert it to meters per second. And if you get time in some different amount, convert it to seconds. And then just throw it in the formula and your acceleration will be in meters per second squared.
Right.
You can do it in different units, but like you can do kilometers per hour per minute. But the SI unit is meters per second squared. So if you just keep everything in meters and
Then it will have
seconds, then yeah, then it'll be fine. Yeah. Okay, here's a little question for you. Anybody here want to be a pilot? Fly planes? Benji? Okay, let's pretend Benji's gonna be a pilot, and he wants to fly planes. And he gets out there, and the airplane has to fly at 71 meters per second in order to lift off the ground. The runway is 1 kilometer long. And so what we're wondering is, what must the plane accelerate at to be able to take off in time?
that's the equation.
Yeah, we're going to use this second equation. If you ever forget, it's right up here. That's number 2. I'll never cover it up. You don't have to memorize it. Oh, he said count. I thought he was saying count. I thought he was saying that. It was you. I get it. We got to change this around, right? Okay, here's practice for you. If you were made mistakes on the quiz, solve this for A. Right now, we're looking for A. Do you have a question? you have a question or do you have the answer? Okay, hold on. Hold on to that answer. For a plane taking off, what is the VI? Good. So our initial velocity is going to be 0. Our displacement we want to change to meters, so that's going to be 1,000 meters. And we're looking for A, right? Okay, so we need to solve this for A. So we're going to subtract VI squared. And then who can tell me what do we want to do next? MC, tell me. Very good. Yeah, I'm going to subtract this term over and then divide by the 2d, and that's going to be A. So our final velocity is 71 squared. That's going to be about 4,900 minus 0 over 2,000. So somewhere like 2.5 or 2.49 or something like that. 2.5? Okay. Around 2.5 meters per second squared would be our acceleration. Now, are we going to build a plane to accelerate at exactly that rate? No. We need way more. Probably like double or triple the amount. Why? It'll work with this. Why can't we just make it that fast?
The runway might be shorter, suppose.
The runway we can make what we want, but what if the wind is blowing against us a little bit? Or what if a dog runs out on the runway and we have to slow down, or we don't want it to be like so. Usually a plane can take it off in 1/3 of the runway that it has. And then if you run into trouble, you've got space that you can slow down in. Who got 2.5? Yay. Okay, last one. Oh, sorry. This is probably the trickiest of the three. Again, it's up there, the third one. So this one is being solved for displacement. It's initial velocity times the time, plus half the acceleration times the time squared. This is weird. What's weird about this formula? There's no final velocity. That's true. Yeah. So you'll notice the second one, what is it missing? Good. This one is missing time. So if you don't have the time, if we don't have time, we're going to use the second formula. What's the first formula missing? Displacement. So if you don't know the displacement, you're going to use the first formula. And if you don't know the final velocity, you're going to use this formula. This is weird because it has time twice. Who here knows the quadratic formula? Okay. If you know it, and you're really good math-wise, and you're really comfortable with the quadratic formula, you can use it to solve for t. If you're not, you never have to use the quadratic. You can instead find the final velocity with formula 2, and then plug it into formula 1, and that'll give you the time. So you can just do it in 2 steps. It's fine and easy. But if you just really want to use the quadratic, you can. Okay, here's a question. I love my food. So if it's hard to see, the scooter, it says the scooter starts from rest. What does that mean? Good. That means VI is 0. And you hit the gas and it accelerates at 1.1 meters per second squared. And then the time is 7 seconds. And the question is, how far does it move? So we're looking for D. So this is really simple plug and chug. You just put those numbers in and calculate. If VI is 0, what happens to VIT? Yeah, this is all gone. So 0 times anything is 0. So we're really just 1/2 times 1.1, was it? Times 7 squared. So 49, 1.1 would be like maybe 54. Half of that is 27, 26 maybe? 27? Somewhere around 27 is what you should come up with. Okay, I'm gonna stop the video and I will post that on the classroom.